Welcome to the Emerson Automation Experts Podcast. I'm your host, Jim Cahill, and today we're focusing on the important role valves, regulators, and actuators play in the mining industry. Whether you run a copper or gold mine, or any other mine for that matter, here's the reality. Valves can't be treated as commodity components. Valves act as reliability multipliers, keeping production stable under harsh duty conditions. Today, I'm joined by Justin Miller from Emerson, who will focus on 4 critical areas in mining operations: slurry management, corrosive chemical handling, remote operation optimization, and water recovery and sustainability. Justin, welcome to the podcast.
Thanks, Jim. Glad to be here.
Well, it's great that you're here. Let's open by asking you to share some of your background and path to your current role here at Emerson.
Sure. I'm a control valve technical specialist with Emerson's Fisher business, and I've spent the last 15 years working hands-on in various industrial applications. My focus is on supporting mining operations worldwide with valve and instrumentation solutions for both new installations and aging assets, working directly with EPCs and mining clients.
Well, that's great background, and we're in a time where mining of everything from lithium to critical minerals to copper and gold, everything else, the world needs a lot of it right now. So let's jump right into our topic. From your perspective, what are the most significant challenges control valves face in the metals and mining industry?
A great start. 4 challenges come to mind, including slurry management, corrosive chemical handling, water recovery, and sustainability, as well as remote operation optimization. Focusing on slurry management first, let's first define what a slurry is. Slurries are fluid mixtures containing both liquid and solid components. The liquid component is not really a particular concern, but the solid component is. That's because those solids can be highly abrasive. Imagine them as sand, rock, even metal. Since control valves are flow restrictions, those solids almost always end up impinging into the valve, causing erosion and in some cases, complete failure. The function of any control valve that makes this damage risk even more concerning is that control valves serve as flow restrictions by design, as that's what allows them to control the slurry after all. Though when the flow is restricted, velocity increases, forcing the solids to then pick up considerable speed as they move through the valve. As the speed increases, so does their potential to cause damage when they ultimately impinge into components within the valve. This damage could force a valve to last as little as a few months, if not days in service, forcing unexpected downtime and expensive repairs. Thankfully, Emerson uses slurry management strategies to combat this damage. First, we consider whether increasing the size of the piping in the valve is possible, as that will reduce velocity into and out of the valve. Second, we optimize the flow path the slurry takes inside the valve to reduce the amount of solid impingement into valve components. Third, we can select hardened construction materials, including ultra-wear resistant ceramics, for the parts of the valve seeing unavoidable solid impingement. Lastly, the bearings that the valve shafts ride on are carefully designed to prevent solids from entering, which would otherwise lead to increased friction and eventually sticking.
Well, that certainly sounds like harsh conditions that we need to help the miners out there manage through. So can you give us a real-life example of how Emerson valves help customers manage erosion, wear, and unexpected downtime in slurries?
Sure. I have an example actually from a gold mine. Specifically, its CIL extraction circuit, which uses cyanide and activated carbon to extract gold from the mined ore. A slurry of calcium hydroxide and water, commonly referred to as milk of lime, is fed into this circuit to maintain just the right pH that prevents formation of rather toxic hydrogen cyanide gas and to ensure high gold extraction. A control valve is used to precisely control this milk of lime slurry. The customer in this case had been using a pinch-style control valve with nothing but problems. First, the valve had poor control resolution at 5%, which made effective pH control difficult, if not impossible. In addition, the abrasive solids in the slurry were causing so much erosion that the valve had to be replaced every 3 months. Yes, that's right. The valves lasted just 3 months. Emerson had worked with the customer to upgrade to its Fisher V150S slurry V-ball control valve, in which case, right out of the box, the customer noticed control resolution was greatly improved from the 5% they had before to just 0.5%. This added precision improved the overall performance of the extraction circuit as tighter pH control was now possible. Next, the customer noticed the need for valve replacement effectively disappeared, yielding savings of $75,000 per year. The Fisher V150S is designed specifically for highly erosive slurries, utilizing ultra-erosion resistant materials in all areas of the valve that contact the process fluid. Those materials include a combination of high chrome iron and ultra-tough ceramic, which give the valve an incredibly long service life at up to 20 years in this one application.
Wow. It sounds like driving that control from 5% down to 0.5% or whatever would make a significant difference in everything that you're doing there. That's fantastic. So is there anything else our listeners should be on the lookout for that causes erosion?
Yes, most definitely. Cavitation is another common source of control valve erosion in mines. To explain, let me start with what cavitation is, because a lot of folks don't understand it. Cavitation occurs only in liquid process fluids and is the result of pressure dropping below the fluid's vapor pressure as it travels through the valve. In a control valve, this typically happens at what's called the vena contracta, which is the point of minimum flow area and therefore maximum velocity. As velocity increases, pressure decreases. And if that pressure falls below the vapor pressure of the fluid, vapor bubbles form. The problem is that pressure then recovers downstream of the vena contracta as flow velocity decreases, which then causes pressure to rise back above vapor pressure, causing those previously formed vapor bubbles to violently collapse. That collapse releases extremely high localized energy in the form of microjets and shock waves. This causes erosion, high noise levels, and severe vibration, all of which scale with flow rate and pressure drop. So then larger valves and higher pressure drops generally mean more severe cavitation damage. From a technical standpoint, we evaluate cavitation using what we call an application ratio or cavitation index, which compares inlet pressure, outlet pressure, and vapor pressure. The higher this ratio, the more likely cavitation, and with it, damage is to occur. From a physical standpoint, cavitation is easy to spot in the field as it produces an iconic sound, sounding as if rocks are flowing with the liquid through the valve.
Yeah, that certainly doesn't sound good for the valve internals, these bubble implosions that are going on throughout there. So what applications then experience cavitation in a mine?
Well, like I said, cavitation can only occur in liquids, in which case the average mine uses a lot of water, making cavitation, quite a pretty good concern for us. It's important to keep in mind that just because the process fluid might be flowing something like water does not mean it's going to behave like the water coming out of your kitchen tap. Under the right conditions, even plain water can cavitate, leading to extreme damage. The good news, though, is that cavitation is predictable. With proper application data and experience, we can determine whether cavitation is mild enough to tolerate or severe enough to require mitigation. In some low-intensity cases, allowing limited cavitation is perfectly acceptable. In higher intensity applications, however, mitigation is a must. One of the most effective mitigation strategies involves staging the pressure drop that the valve must take. Instead of taking the full pressure drop at once, specially engineered valve trim divides the pressure drop into multiple steps. This prevents the fluid pressure from ever falling below the vapor pressure, eliminating the formation of vapor bubbles, and with it, the cavitation. There are trade-offs in such a design, as typically it reduces flow capacity, requiring a larger size valve compared to one without this type of technique. Another technique to consider is called aspiration, which mitigates the negative effects of cavitation with very little impact on flow capacity. With proper understanding of the application, we can determine which cavitation mitigation technique is best.
Yeah, that aspiration technique sounds interesting. Can you share an example of where Emerson valves have helped customers manage the erosion, noise, and vibration associated with cavitation?
Certainly. I have an example actually from a potash mine, in which case, those not familiar with this type of mining, let me start with a little background. Potash refers to a grouping of potassium-rich salts found deep underground that are then used to make fertilizer, among other various products. Potash is extracted using water, since as a salt, well, it dissolves into water. To do that, raw water is pumped underground into a well, where it sits to allow the potash to dissolve into it. After a period, this solution of potash and water is then pumped back above ground, where the potash is further processed out. One of the many raw water control valves that this mine in my example was using had been originally selected as an otherwise standard 14-inch Fisher V-ball segmented ball valve. Though after the mine was built and running, they noticed some problems. The first was that the entire valve assembly was severely vibrating, which, as you can remember from earlier, that's a symptom of cavitation. The second problem was that this vibration was damaging the valve actuator, specifically its electronics, leading to frequent repairs. The third problem was erosion at the outlet piping, needing frequent replacement. Those problems cost the mine nearly $40,000 per year in just replacements and repairs, and those occurred every 2 to 3 years. Upon closer inspection, it was discovered that the valve's pressure drop was much higher than what it was expected during initial engineering. With these now higher pressure drops, severe cavitation was then predicted. This, along with the field observations of vibration and erosion, revealed cavitation as the cause of these problems. The cavitation mitigation technique of aspiration was considered, as it kept flow capacity unchanged and allowed the customer to keep their current valve setup. This technique called for a small pipe to be inserted into the outlet pipe along with a check valve on top. Then as cavitation occurred, the below atmospheric pressure at the vena contracta inside the valve would drive a small amount of atmospheric air in. This air then cushioned the effects of cavitation, greatly reducing its severity and the resulting vibration. So much so that this customer realized an extension in the lifespan of this valve from as little as 2 years before to as much as 8 years. This resulted in a savings of nearly $25,000 yearly for the mine.
Wow, that's really something, the amount of damage caused by that cavitation from something as simple as water that was moving through there. So I guess let's move on to the next challenge of corrosion chemical handling. What does that entail?
Well, let's start with the water we just talked about. It'll certainly corrode or otherwise rust carbon steel materials, which are fairly common and, obviously because they have great strength and are relatively economical. The industry uses quite a few carbon steel valves in water systems with often good success. Though if cavitation or another erosive condition occurs and goes unmitigated, it can wash away this rust from the valve. That then introduces a cyclical condition known as corrosion, erosion, that can lead to rapid material loss. So then if erosion is expected, it's best to upgrade the material to one that will not corrode, such as a chrome moly alloy steel. There are, though, far more corrosive fluids in the average mine than just water. Case in point, acids, including sulfuric acid, are often used to break down and liberate minerals from ore. We all know that acids like those are corrosive, in which case plastic-lined carbon steel or iron valves are popularly used, where the plastic lining protects the steel or iron material from corrosion. Though that only works well for non-erosive applications, as the plastic lining just isn't very durable. Erosive and corrosive applications would then do best with unlined valves, in which case, depending on the fluid, its concentration, and temperature, we could see anywhere from duplex stainless steel to nickel alloys in order to combat corrosion while still standing up to erosion.
Cool. Wow, it's great to have some of those alloys that can handle those very corrosive applications. So with all these corrosive fluids, I'd imagine packing leakage is of great concern. Is it?
You're spot on. Even small amounts of packing leakage in a highly corrosive application can create quite the damage around the valve. Just consider that any leakage will eventually drip onto the actuator, instrumentation, pressure retaining bolting, or onto nearby equipment. Worse yet, it poses a real safety concern for workers. Even if the valve packing is tight at first installation, it'll most certainly leak as the valve ages over time. This is due to the operation of the valve just simply wearing out the soft parts of the packing that are critical to its tight sealing. That is, those parts wear, the compression of the packing decreases, and with less compression, the packing leaks more. To address this, a live-loaded packing system is often used, which introduces springs to compensate for this wear, making for a longer-lasting, tight seal. To ensure the packing is tight, ISO 15848-1 type testing and certification of the packing system is best. This standard establishes both a testing process and leak performance criteria for the valve packing. It even has test criteria to evaluate how leak rates may change as the packing takes on cycles, similar to it being used in a real-world mining application.
Well, that's great that we can attack that packing challenge. So I suppose this brings us to the next challenge you mentioned of water recovery and sustainability.
Definitely. So we can't forget that mines use many valves to control water, and often water is a scarce resource. Just like a leaky faucet in your home, it may not cost you much on a day-to-day basis, but you're definitely going to notice it on your monthly water bill. So that a high-performance valve packing tested and certified to that ISO 15848-1 standard, even on a water service, is an excellent idea to reduce water makeup costs. Many other fluids, though, are harmful to the environment and mine personnel if they leak from the valve packing. Let me give a few examples. So in gold and silver mining, we use often cyanide solutions to leach the metal from the ore. Cyanide, though, is very toxic to the environment as well as personnel. So tight valve packing, if not a zero-leak bellows seal technology, is a must-have. Copper mining commonly uses sulfuric acid for leaching, just like gold mining. Being an acid, any leakage threatens severe corrosion to equipment. Though outside of that, leakage will also introduce risk to personnel, as well as cause damage to nearby aquatic ecosystems. If those are not concerning enough, we have to keep in mind that all leakage is waste, and waste goes directly against sustainability goals.
Yeah, we certainly need to attack those sources of leaks for the environment, for the personnel, for the equipment that can rot away from the acid. It's a tough industry there. So what remote diagnostic capabilities should mining operations prioritize to improve reliability and plan maintenance proactively?
Sure. Well, Emerson has many smart instruments that can diagnose not only issues with the instrument itself, but also issues with the broader valve assembly. Let me paint an example. Let's say we have a ball valve controlling a slurry with very small sized solids. These solids will then most certainly enter the tight clearances between the shaft and the bearings of the valve. Those make up the valve's drivetrain. Over time, the solids will likely wear down the surfaces of those parts, increasing their friction, which then degrades control resolution. This is usually a gradual degradation over time, in which case, if left unaddressed, it can lead to complete seizure of the valve. A smart valve controller like Emerson's Fisher FieldView DBC 6200 provides the ability to remotely measure and trend over time the friction of the valve's drivetrain. This can then help the user determine if service is needed and, more importantly, how long they may have before enough degradation occurs to impact operations. Conversely, the drivetrain in this control valve example could have been just as easily degraded by corrosion due to improper material selection. This happens from time to time and can be caused by process fluid chemistry changing without a careful check of whether the valve components remain compatible.
Yeah, that's really an important point about the intelligence in those digital valve controllers to spot problems early and address them before things happen that are not good. And so, can any of these smart instruments also be used for on-off valves like they are for control valves?
Great question. Just like control valves, on-off valves will also see challenges that contribute to their gradual, or in some cases, not so gradual degradation. We just talked about abrasive slurries wreaking havoc on control valve drivetrains. Just like a control valve, these on-off valves also have drivetrains that must be in good condition in order for the valve to work properly. Measurement of friction is not practical, though, for an on-off valve because it only moves between endpoints, which prevents an accurate friction measurement. Though we can still measure drivetrain degradation another way. That is by measuring the stroke time each time the valve is operated. As the drivetrain is degraded, this stroke time will get longer and longer. Emerson's Fisher FieldView 4400 position transmitter is a smart instrument that will measure this stroke time. This instrument will then compare that to a user set threshold, generating an alert when that threshold has passed, signaling when the drivetrain needs servicing. However, what if we had a valve controller for an on-off valve? It's commonplace in the control valve world to have a single instrument such as that to handle control of the valve, diagnostics, and position feedback. Why not then reap those same benefits for on-off valves, especially those in challenging services? One such device is Emerson's Fisher FieldView DVC 7K valve controller. This smart instrument offers a local user interface, allowing easy setup and calibration. It'll even tell you when it diagnoses a problem with a convenient status light as an indicator. Then, with a few button presses, it'll tell you what the cause of the problem might be, making for quick troubleshooting.
Yeah, you think of on-off valves just sitting there. Well, in the case of a safety valve that may not operate for a long time, but even ones that are used in there, that's a clever way to see if it's doing well, measuring that stroking time, if it's starting to struggle and get there and give early enough indication so it can be addressed again before you get to abnormal conditions. Well, Justin, I want to thank you for these great insights. So where can our listeners learn more about these Emerson valve solutions that we've discussed?
Sure. It was a great pleasure speaking with you, Jem. So for our listeners, they can learn more about our valves, regulators, and actuators specific to mining by visiting emerson.com/mining valves.
Justin, again, I want to thank you for sharing your expertise with our listeners today.